Exploring planets, nebulae, and interstellar objects is truly a thrilling opportunity that the James Webb Space Telescope has opened for us. But the main motivation behind its construction actually came from a slightly different branch of space science. In this second part of the review of Webb's third year of discoveries, we dive into the early universe, where astonishing objects continue to surprise us. In the section on black holes, we'll watch Sagittarius A star flicker and discuss what may be the first evidence for the birth of a supermassive black hole through the direct collapse of gas clouds. Finally, we'll stop by the solar system, which also had no shortage of fascinating events that Webb revealed in exquisite detail. So, get comfortable. Let's begin. And I think it makes sense to start with the fact that James Webb has once again set the record for the most distant object in the universe ever observed. This is MOM-Z14, announced in May 2025. Its spectroscopically confirmed redshift is 14.44, which means we're seeing this object when the universe was only 280 million years old. The previous record holder, GSZ14, discovered last year, had a confirmed redshift of 14.18, so Webb has essentially broken its own record. The properties of this galaxy, and yes, spectroscopy confirms it is indeed a galaxy, show that it's only about 500 light-years across, making it extremely compact. But at the same time, it's extraordinarily bright, which means all that emission is concentrated in a very small area. Naturally, compact luminous objects tempt one to think of a quasar or an active galactic nucleus. But no, the astronomers rule out the idea that all this brightness comes from a supermassive black hole devouring matter. The spectrum of this object simply lacks the telltale signs of an accretion disk, so it seems that the light is coming from young, brilliant stars. This makes MOM-Z14 yet another oddball of the young universe. Its brightness suggests a stellar mass of over 100 million suns, comparable to the small Magellanic Cloud. And this is something researchers absolutely did not expect to see so early in cosmic history. In fact, the name MOM is short for the survey it comes from, Mirage or Miracle. This survey was designed specifically to spectroscopically test many of the bright objects Webb spotted within the first 500 million years of the universe. Since this new record holder turned out not to be a mirage but a genuinely bright galaxy, then in astronomy terms, it's a miracle. Once again, no one expected such bright galaxies with developed basic structures to exist just a few 100 million years after the Big Bang. And yet, even these were not the very first. The spectrum of MOM-Z14 contains lines of carbon and nitrogen, heavy elements forged through nuclear fusion in stellar cores, which means at least one generation of stars in this galaxy had already lived out their short lives and exploded as supernovae, scattering these elements into space. Therefore, there must be even earlier galaxies than this one, galaxies whose spectra will show only hydrogen and helium. Whether Webb's sharp infrared vision will reach them remains to be seen, but astronomers are certainly hoping it will. By the way, the previous record-holding galaxy, JWST Z14-0, also stunned astronomers with its chemistry. In March 2025, two independent teams reported the discovery of oxygen in it. Just like carbon and nitrogen, oxygen is a marker of chemical maturity in a galaxy. And the concentration turned out to be so high that this galaxy likely already had enough heavy elements to start forming second-generation stars, stars like our Sun, or even red dwarfs. The idea is that such relatively small stars couldn't have formed in metal-poor environments, because pure hydrogen-helium clouds simply couldn't cool efficiently enough to collapse into tiny clumps. That's why the first generation of stars is thought to have been extremely massive. The chemical conditions just weren't right for birthing dwarfs. On top of that, the presence of heavy elements in GSZ14 means that, at least hypothetically, the earliest steps toward planet formation could already be happening there. Imagine rocky, Earth-like worlds in a universe just 300 million years old. What would that mean for the possibility of life starting and surviving so early? And here's an important detail. Oxygen wasn't discovered with Webb this time, but with the ALMA radio interferometer in the Chilean Atacama Desert. The oxygen spectral lines allowed scientists not only to confirm the element's presence, but also to reconfirm the galaxy's redshift. its age, and actual distance. So this really is one of the oldest galaxies we've ever seen. The catch? It contains 10 times more heavy elements than leading models predict. It seems early galaxies not only formed far faster than expected, but also evolved chemically at an astonishing pace. Of course, these are far from Webb's only strange finds at the dawn of the cosmos. For example, how about a galaxy with a bulge, a disk, and spiral arms, almost the size of the Milky Way, but at a redshift of 5.2, just 1 billion years after time began? This ancient twin, or near twin, of our galaxy popped up in Webb's data completely by chance as part of a sky survey called Panoramic. This is a special observing mode. While one of Webb's instruments focuses on a target, another takes wide-field images of the surrounding sky. That way, astronomers can map patches of the cosmos in high resolution and later hunt for interesting surprises. And this object was exactly that, a surprise. Its morphology is stunning. The disk stretches over 60,000 light-years, compared to the Milky Way's diameter of about 100,000. Yet in mass, the newly discovered galaxy rivals ours, with an estimated 100 billion suns worth of stars. And as you've probably guessed, spiral galaxies weren't supposed to exist this early, at least not according to current models of galaxy evolution. Our Milky Way is thought to have taken billions of years of mergers with other galaxies to build up its stellar mass, and it's still at it, slowly consuming dwarf neighbors. But how this ancient galaxy managed to reach such scale in just a few 100 million years, that's a very good question indeed. In fact, it's not the only one of its kind. In November 2024, the same team announced the discovery of at least 3 more galaxies they nicknamed the Red Monsters. That's because each of them also weighs in at around 100 billion solar masses and existed when the universe was only about 1 billion years old. So, where did they all come from? The discovery team believes the answer lies in efficiency. The standard picture is that galaxies form within giant halos of dark matter, whose gravity pulls in normal matter. These clouds of gas collide, form stars, but not all of the gas actually turns into luminous objects. Star formation is generally considered an inefficient process. Only about 20% of a cloud's original mass becomes stars. We know this from nearby examples. For instance, in the Orion Nebula, the mass of newly formed stars is only about 15 to 20% of the local gas. Sure, star formation is still ongoing there, but at the same time, much of the gas gets blown away by powerful stellar winds from massive newborn stars. In the end, the efficiency still settles around 20%. But the discovery of these red monsters suggests that about 40 to 50% of their initial gas clouds turned into stars, twice the normal efficiency. Where does that come from? As you've probably guessed, there's no clear answer yet. Maybe in today's universe, 20% is typical, while in the first billion years, 50% was the rule. Or maybe some other astrophysical processes are at play, explaining why these particular galaxies appear so bright and massive. Likewise, maybe similar processes explain the brightness of ancient galaxies at record-breaking redshifts. But for now, the truth is this. The deeper Webb looks into cosmic history, the more surprises come into view. And that is the real value of this telescope, not just confirming our theories, but showing us things that force us to refine them, or in special cases, to rethink them entirely. That said, I'd strongly caution against interpreting every new discovery as the end of modern cosmology, or anything like that. I know many people lean toward alternative models of the universe, and that's fine. But nothing Webb has shown us about the early cosmos so far suggests that the Big Bang theory itself is in jeopardy. Not all new objects have anomalous sizes, brightness, or masses. On the contrary, most galaxies at the dawn of the universe look just as astronomers predicted, though among them, there are indeed some strange outliers. That's no coincidence, and scientists certainly have their work cut out for them. But it doesn't mean it's time for dramatic declarations about rewriting the origin of the universe. Maybe one day that moment will come. But for now, it's too early for such conclusions. Science doesn't work that way. Well then, let's move on to what you could call the Middle Ages of our universe. A time still full of mysteries that a telescope as sensitive in the infrared as Webb can help unravel. One such mystery is the curious structure of our own galaxy. When you look at those beautiful time lapses of the night sky with the Milky Way, you're not just seeing a stripe of stars. Our disk galaxy is actually structured like a layered pancake. The thing is, the Milky Way, and many other spirals, is really made up of two disks. A thick one, populated by older stars, and a thin one, home to younger generations, including our Sun. To be more specific, the thick disk is about 3,000 light-years tall, while the thin disk embedded within it is no more than 1,000 light-years thick. Yes, the two are linked, but their stars differ a lot, not just in age. Most of the thick disk stars are old and metal-poor, meaning they have very few heavy elements, which suggests they formed early in the galaxy's history. Meanwhile, the thin disk stars are younger and richer in metals, which points to later star formation out of material already enriched with heavy elements. The thin disk also contains plenty of gas and dust, with star formation still ongoing, unlike in the thick disk. Finally, the stars in these two structures behave differently. Those in the thin disk orbit the galactic center in neat, almost circular paths, while in the thick disk, stellar orbits are more tilted and chaotic. But where did this double structure come from, and how exactly did it form? Using Webb, a team of astronomers tried to get closer to an answer. They studied 111 disk galaxies seen edge-on, spanning a wide stretch of cosmic time. For the first time, they spotted both thin and thick disks at distances over 10 billion light-years. That's not easy, since the faint stars of the thick disk usually get drowned out by the glow of the thin disk's bright young stars. Here, Webb's ability to peer through dust and pick out faint ancient stars proved invaluable. The team began by sorting the 111 galaxies into two categories, those with only one disk and those with two. And they found that single-disk galaxies resembled thick disks. This suggests galaxies first formed thick disks before developing both structures. There are several possible scenarios, but the most likely, according to astronomers, is the turbulent gas disk scenario. In the early universe, galaxies were gas-rich, and that gas was hot and dynamic. Stars had to form in these unstable conditions. The chaotic motion of newborn stars naturally led to wide, scattered orbits, and thus a puffed-up thick disk. But over time, accretion slowed, turbulence faded, and cooler gas settled toward the central plane of the thick disk. In this calmer environment, a new generation of stars formed, with more orderly orbits, giving rise to the thin disk. Importantly, the thin disk didn't replace the thick one, but embedded itself within it. That's why spiral galaxies like ours now carry a double disk structure. To check their hypothesis, the team turned to ALMA's archival data, the same ground-based radio telescope network we mentioned earlier. The results showed that galaxies at higher redshifts do indeed have higher gas turbulence. This supports the idea that the thick disk really is the first evolutionary stage of galaxies like the Milky Way. The astronomers also managed to estimate how quickly one disk turns into two. It turns out this depends on the galaxy's mass. More massive ones made the transition around 8 billion years ago, while smaller ones only did so about 4 billion years ago. So, the past of our own galaxy is coming into sharper focus. By studying galaxies across different eras of the universe, researchers are piecing together how the Milky Way evolved, from a young, chaotic system into the mature spiral galaxy we see today. Perhaps the highlight of Webb's third year, at least in my opinion, has to do with supermassive black holes. I even debated whether this story deserved its own separate episode, but let's explore it here. In short, it looks like astronomers may have found the first evidence of a direct collapse of gas clouds into a supermassive black hole. This has long been one of astrophysics' great puzzles. Where do the black holes at the centers of nearly every galaxy come from? More precisely, how do such enormous black holes form? Millions and sometimes tens of billions of times more massive than the Sun. One popular scenario suggested they originated from the collapse of the first stellar cores, in an early universe where the very first stars could be hundreds of times more massive than the Sun. Later on, these relatively small seeds would have grown by swallowing matter and merging with each other, eventually becoming the giants we see in galactic centers today. But that explanation is no longer the favored one, because the early universe revealed by Webb doesn't quite play by the expected rules. In last year's review, we talked about the discovery of extremely massive black holes in the first billion years of cosmic history. Just like many galaxies of that era, these objects seemed too mature, too massive, to have gained all their mass simply through mergers and accretion. Quite simply, they didn't have enough time, which naturally forces astronomers to consider other explanations. And one of them is that monsters were born as monsters, right from the start. Simulations have shown that in the very early cosmos, some gas clouds, still free of heavy elements, could avoid fragmenting into multiple dense clumps and instead collapse entirely under their own gravity. In such cases, the collapsing core could become dense enough to skip the stellar phase entirely and turn straight into a giant black hole. Computer models say this is possible, but of course, seeing such an object in the real universe would be far more convincing. One of Webb's large sky surveys is called Cosmos Webb. Recently, astronomers analyzing its vast troves of images found something intriguing: a galaxy with a double core, clearly the product of two galaxies in the process of colliding. What's striking is that both galaxies resemble ring galaxies, with bright cores and surrounding rings of young stars. Because of its shape, the Discovery team nicknamed it the Infinity Galaxy. The two are colliding almost edge-on, meaning their disks are nearly parallel. At the point of impact, you can spot a bright patch, evidence of intense star formation. Astronomers studied this region carefully across many wavelengths, not just with Webb, but also using the Keck telescopes, the very large array of radio antennas, and even the Chandra X-ray Observatory. And here's the kicker: they found a strong radio source, along with significant X-ray emission, classic hallmarks of a supermassive black hole. Accretion disks around such black holes shine brightly across the spectrum, as matter swirls at relativistic speeds and heats up through friction to staggering temperatures. That simply doesn't happen in ordinary bursts of star formation. The ratio of radio to X-ray luminosity in this system matches perfectly with what's typically seen from active black holes in the range of tens to hundreds of millions of solar masses. On top of that, both galactic cores also host black holes, which means the two galaxies together contain not two, but three black holes. So astronomers are confident about what they're seeing, but a big question remains. How did one of these supermassive black holes end up not in a galactic center, but right between two colliding galaxies? Its location, exactly at the point of impact, where gas clouds slam into each other and compress, hints strongly at one particular scenario. The Discovery team suggested that this might be the first observational evidence of a black hole forming through direct collapse of gas clouds. As we know, when galaxies collide, their stars rarely crash into one another. Gas and dust clouds, however, do collide head-on. If the impact is violent enough, the pressure can create an extremely dense clump of gas, dense enough to collapse straight into a black hole. And interestingly, many astrophysicists think such extreme densities were actually quite common in the early universe, back when galaxies were just beginning to take shape. Could it be that in the Infinity Galaxy, astronomers are witnessing a similar process unfold before their eyes? Of course, extraordinary claims require careful checks. Before declaring a black hole born from direct collapse, they had to rule out other possible explanations. At least two alternatives came to mind. First, this could be a so-called runaway black hole. Astronomers have found such objects before. They can be flung out of their galaxies through complex gravitational interactions, especially involving three black holes at once. Or, if two black holes merge with very different masses and spin rates, the newly formed remnant can be ejected by a powerful gravitational wave recoil. Second, the object might belong to a third, smaller galaxy that just happens to sit in the same patch of sky. But astronomers searched carefully and found no trace of such a galaxy. And besides, dwarf galaxies are not known for hosting supermassive black holes of this scale. That left one decisive test. If the black hole truly formed right inside these colliding gas clouds, its motion should be perfectly tied to the gas itself. In other words, its velocity should match that of the surrounding material. So the team requested more observing time with Webb to measure the region's dynamics. Using spectroscopy, they measured the radial velocity of the bright gas patch and then compared it to the velocity of ionized gas linked to the black hole. From this, they could indirectly estimate the black hole's own motion. And the result? The black hole fit beautifully into the velocity pattern of the surrounding gas, exactly as if it had been born there. This was the key piece of evidence. The odds of it being a chance interloper now seemed extremely low. The authors stress that they can't yet make a definitive claim of having caught a direct collapse black hole in the act, but they are determined to continue studying this remarkable system. If their interpretation holds, it would mark a major breakthrough in astrophysics, the first direct observation of a black hole's birth through this unique process, finally providing an answer to a problem that has lingered for decades. What was once only theory and computer simulation may now be crossing over into the realm of direct observation. At the heart of our own galaxy lives a supermassive black hole. It's one of the most legendary objects in astronomy, simply because, understandably, it's been studied more than almost any other. Many of you have asked in the comments whether James Webb could peer through the gas and dust at the galactic center to capture Sagittarius, a star. The short answer? No. Unfortunately, Webb can't take a picture of it the way the Event Horizon Telescope did, since its resolution just isn't high enough. But studying its behavior, that Webb can absolutely do. In fact, our black hole has been observed across a wide range of wavelengths. In the near-infrared, for instance, it's been monitored by observatories like Keck, the Very Large Telescope, and space telescopes like Spitzer and Hubble. Near-infrared emission is especially important because its variability carries crucial information about the dynamics of gas in the innermost part of the accretion disk, where superheated material is spiraling down onto the black hole itself. These past observations hinted at intriguing flares lasting from minutes to hours, and possibly other types of variability in the disk. But the data was always messy. The galactic center is so crowded with stars that disentangling the black hole's activity from its turbulent surroundings proved difficult. Here, Webb has a clear advantage over ground-based telescopes. It can continuously monitor the region for long stretches, observe at multiple wavelengths simultaneously, and of course, it offers better resolution than its space-based predecessors. And so, in February 2025, a team of astronomers published the results of 48 hours of Webb observations of Sagittarius A star. These weren't a single marathon session, but a series of 8 and 10-hour continuous monitoring intervals spread across the year. As the researchers themselves put it, they expected to see some flares, but not nearly the level of activity they actually found. What emerged was essentially a non-stop fireworks show, with bursts of different durations and intensities. The accretion disk was generating 5 to 6 major flares per day, along with a constant low-level flickering every few seconds. On top of that, astronomers detected longer-term brightness changes playing out over months. Exactly what drives all this activity remains unclear. This is the first time we've ever seen such a detailed profile of a supermassive black hole. But the team does have hypotheses. They argue that short and long flares likely arise from two separate processes, though both are tied to the motion of plasma and the magnetic fields created by it. For instance, the faint, rapid flickering may be caused by turbulent plasma oscillations in the disk, which compress the material and trigger brief radiation bursts. The researchers compare this to solar flares on our sun, caused when magnetic field lines reconnect and erupt. Though, of course, the scale near a black hole is vastly more extreme. As for the longer-lasting flares, the authors again point to magnetic reconnection, when two magnetic fields collide, releasing bright jets of particles moving at nearly the speed of light. All of this is brand new insight into supermassive black holes, and scientists are only beginning to unravel the physics of their accretion disks. Sagittarius A star is naturally our primary laboratory for studying these cosmic heavyweights, and Webb has already revealed that those neat, polished animations of black holes aren't quite accurate. The reality is much more explosive and chaotic. The authors of this study are just getting started with the data and are hoping to secure more Webb observing time to continue probing the core of our galaxy. From the core of our galaxy, let's shift to our home star system. During Webb's third year, a few interesting events unfolded within the solar system that called for time on our flagship space observatory. First up is the asteroid that went viral online, 2024 YR4. Discovered at the end of 2024, its orbit immediately raised concern among astronomers because it seemed to pose a potential threat to Earth. Early estimates even suggested a few % chance of a collision in 2032. But soon after, more precise observations showed that the risk to Earth was practically zero. Instead, the remaining concern was a possible encounter with the Moon. To pin down the object's properties, Webb was pointed at it in late March 2025. At the time of this recording, it's the smallest object JWST has ever targeted, and one of the smallest whose size has been directly measured. Most observatories can only detect sunlight reflected off asteroid surfaces, but Webb's infrared vision can measure the object's thermal radiation. Using NIRCam, astronomers first measured the reflected light, then followed up with MIRI to capture its heat. This allowed them to determine not just the asteroid's size, but also the composition of its surface. It turns out the asteroid is about 60 meters in diameter, give or take 7. For comparison, that's roughly the size of the famous Tunguska impactor. It's also much smaller than Dimorphos, the asteroid successfully nudged by NASA's DART mission, which means that rocks of this size could be deflected without too much trouble, provided they're detected early enough. YR4 will swing past us again in 2028, giving astronomers another chance to refine its orbit. By then, we may know for certain whether it will strike the Moon. For now, Webb's data nudged the probability slightly upward, from 3.8% to 4.3%. We'll just have to wait and see. But perhaps the bigger headline in our solar system this year comes from the discovery of a brand new interstellar visitor, 3I Atlas. At the time of this recording, the story is still unfolding. The object is traveling sunward, currently somewhere between the orbits of Jupiter and Mars. Despite plenty of wild speculation, most astronomers agree this is a comet, not a spacecraft, as some dreamers hope. On August 6, 2025, Webb turned its eye on Atlas for the first time, observing it in the near-infrared. The main goals were to determine its size, physical properties, and, most importantly, its chemical composition. As expected, the comet is becoming more active as it approaches the Sun. Its spectrum revealed traces of carbon dioxide, water, water ice, carbon monoxide, and other molecules. The real surprise was the amount of carbon dioxide. Specifically, the CO2 to water ratio turned out to be several times higher than what we typically see in solar system comets. This strongly suggests that Atlas's nucleus is unusually rich in CO2. Astronomers studying the data point to the conditions in which the comet formed back in its native system. In protoplanetary disks, the birthplaces of comets, asteroids, and planets, chemical reactions on dust-grained surfaces play a key role in determining composition. For instance, reactions between CO and OH can favor the production of either CO2 or H2O, depending on the environment. In the dark, shielded regions of molecular clouds, water usually dominates. But under the influence of ultraviolet light or cosmic rays, models show that CO2 production can win out. So one possibility is that Atlas formed in a more radiation-rich environment than comets born here. The team emphasizes that more modeling will be needed to connect the observed CO2 abundance with the comet's origins. It's worth remembering that Atlas likely came to us from the thick disk of the Milky Way, where stars tend to have lower metallicity. In any case, the investigation of 3I Atlas is just getting started. By the time it departs back into interstellar space, this comet will carry far fewer mysteries than it does today. One more major discovery with Webb was announced literally as I was putting this video together. The seventh planet from the Sun, icy Uranus, has revealed a brand new moon. That makes 28 turn into 29. The new satellite was detected in a series of 10 exposures, each lasting about 40 minutes, taken with Webb's near-infrared camera. It's tiny, around 10 kilometers across, assuming its albedo is similar to Uranus's other moons. That small size likely explains why Voyager 2 missed it during its flyby back in 1986. For now, the moon doesn't have an official name. The International Astronomical Union still has to confirm it. but most likely it will follow the tradition of Uranian moons and be named after a character from a Shakespeare play. Meanwhile, over at Neptune, Webb has captured polar auroras for the very first time. Astronomers had long suspected they were there, since auroras have already been seen on the other outer planets. But it took Webb's infrared sensitivity in the near IR range to finally reveal them. And as you can see, Neptune's auroral activity looks very different from what we're familiar with on Earth, or even on Jupiter and Saturn. On Neptune, auroras appear in mid-latitudes. That's because the planet's magnetic field is tilted a full 47 degrees from its rotation axis. Still, the bigger mystery remains. Why is Neptune's magnetic field so strange, and where does it come from? To get closer to an answer, researchers plan to monitor Neptune with Webb throughout a full 11-year cycle of solar activity. For now, we can only dream of full-scale missions to the ice giants. Until then, observatories like Webb and future ground-based giants with adaptive optics are our best chance to study these worlds in detail. In fact, Webb's infrared sensitivity has just opened up a brand new window. It revealed the ionospheres of Uranus and Neptune for the first time, in unprecedented detail. And with that, friends, I'll wrap up this overview. Just a reminder, this is part 2. If you haven't seen part 1 yet, I invite you to check it out. Meanwhile, inspired by the ice giants, I'll be preparing a dedicated episode on one of them. And you, in the meantime, can support me with a like and by leaving a comment. Thanks for watching till the end. See you in the next episode, and take care of yourselves.